Alright, we are starting and we continue what we have started last week, so it means the Debye model. Now, in the Debye model, I just remind you, again, we assume that we have a solid. In this solid, we have many atoms. Those atoms are somehow vibrating. Okay, and we found out that the Einstein description of the solid was erroneous in the limit of small temperatures. Okay, so in the limit when t goes to 0, there was something wrong about the Einstein description of the solid. Now, what is the prescription of Debye? How to solve this problem? So Debye said the following thing. Number one, what are miscalculations or erroneous assumptions that were introduced by Einstein? Not one single model is vibrating, but actually all the different particles are vibrating in groups. Basically, he said we have waves inside the system and not just vibration of single particles. The different particles or groups of different particles are vibrating somehow. Now, if we have waves, so the total description is some sort of description by superposition of waves. Now, in superposition of waves, we don't really consider interactions between the different waves. So this is how Debye wants to overcome this issue of correlations between different motions of different particles. Right? Einstein simply assumed, well, I neglect any interactions between different particles. Debye said, well, I introduce interaction, but I introduce this interaction is in a way that all the particles are creating waves, but the different waves are not interacting between themselves. Right? So particles do interact, waves do not. Next thing, okay, is two things that we need to perform. First, can we indeed describe this in terms of waves? Right? This is number one. B is the moment that we have waves, I started to describe to you that we have some sort of might have some continuous representation of the frequencies of those waves. Right? So let's see how those two ingredients come inside the theory. Right? So Debye assumed that his Hamiltonian is something like 1/2 m over I and over j. Over I and over j, x, I, and j, dot squared, plus some potential energy which is x11 and x12 and x13 and x21. Some huge interaction between all the different particles. Now, I goes from 1 to n. I, 1, 2, 3 to n, which is the number of the total particles that we have inside our system. J, the subscript j, goes from 1 and 2 and 3. Those are the different coordinates. Right? Each particle can have a motion in the x direction, y direction, z direction. Okay. Okay. Next step is to write it down instead of using I and j notation and simply saying, well, let's forget about I and j notation. Right? Let's write everything down in terms of k. Right? What is k? K goes from 1 to 3n. I'm basically looking on n or on each xij. Over here I'm saying, well, this is a degree of freedom. And in total I have 3n degrees of freedom. So I will have an index which runs from 1 till 3n. Let's call it x tilde dot squared k. Okay? And my potential, as over here, right, the potential energy is dependent only on the different degrees of freedom. I don't care if it's exactly x11 or x21, etc. I'm just writing it down as u of x tilde 1, x tilde 2, x tilde 3, up to x tilde 3n. In total, I have 3n degrees of freedom. Okay. Now, of course, we cannot solve this problem entirely because we do need to know exactly what this potential energy is, right? So we never know, we never do. Now there is a usual physical assumption. The assumption is that we will write this as in a quadratic form. So we do not neglect interactions. We do not neglect interactions between the different particles, but we take into account only what? Some fluctuations or deformations about the minima. There is a minima to this potential, and when we expand this potential in a Taylor series in 3n coordinates around this minima, okay, we take into account only the quadratic terms. Right? The assumption of Debye that we do not need all the potential, but we are sitting somewhere below or near the minimal energy all the time, and the only thing that we need to take into account are the quadratic terms. Right? So in some sense that we are assuming that we have a lot of particles that are connected by springs, right? But they all interact with each other. So this particle somehow interacts with that particle. Okay? This is not neglected. When I do this, okay, the kinetic energy stays the same. So it's still 1 over 2m, a sum over k from 1 to 3n, x tilde dot square k. And I have here a representation which is a sum over L, a sum over n, 1/2 du dxl dxn, and here I have xl and xn, okay, in total. So this is the expansion, and I assume that there is some constant u0, which is the minima of my potential energy. Okay? So this is an expansion, or this is an expansion of my total potential energy, and I expanded around the minima. Great. Now I want to write all of this in a vector form. Okay? It's going to be a little bit easier to consider everything that when we have a vector form. So I have this zeta, which is x tilde 1 and x tilde 2 and x tilde 3 up to x tilde 3n. Okay. So when I have this vector over here, I can write everything as, okay, this as 1/2 m z tilde dot, oh, so this is the vector, right? That, not tilde, dot, z tilde transpose. Okay, so this is just a sum over all derivatives of this vector, okay, plus z vector multiplied by a multiplied by z transpose plus some u0. Okay. So instead of writing all of this with some summation indices, etc., I'm using the vector notation, and I'm saying, well, this is a vector multiplied by its transpose. So this is just a sum. Here I have the vector multiplied by A, which is a matrix, okay, multiplied by the transpose of the same vector. And what is this matrix? So Aij equals to 1/2 du dxi dxj. Yes.
רק לא הבנתי את הדלת של הנגזרת בשורה השלישית.
Where?
גזרנו פעם אחת.
This or this? What is the problem? This?
לא,
This?
לא, כן, כאן בסכום.
Yes.
אז הנגזרת שם אני גוזרת פעם אחת לפי xn, ואז הפעם השנייה, איך אני גוזרת את זה?
So you have to take a derivative with respect to xl and xn. They can be exactly the same So this is tilde over here. They can be exactly the same variables, or they can be different. Yes, it's a second derivative. Dou squared. That's the problem? When you expand in Taylor series, right? If you have a function, u of x. So you say I expand around my minima. So this is u0 plus du to dx multiplied by x plus d squared u to dx squared multiplied by x squared. Now, since it's a derivative or its expansion around the minima, this term goes away, and we are left only with the second derivative. Okay.
The transposes aren't supposed to be on the left.
You want it to be the other way around?
Yes, because otherwise it's a matrix, not a number.
Okay. So I don't want to change this. I will change this. Then it's fine?
Yes.
Yes.
The zeta in the negative kinetic also supposed to be a derivative.
A derivative?
Yeah, this was.
Oh, this guy. Yes, thank you. Thank you. Okay, anything else that I have missed? All right, now, the thing to remember, this A, look on this form, it's a symmetric function. Okay, it's a symmetric function. So what does it mean? It means that A as a matrix, okay, I can describe it as SD S minus 1, where S matrix of eigen vectors of A, D diagonal matrix with eigen values of A, and S minus 1 equals to S transpose.
What is eigen?
Eigenvalue, אנחנו מצמיעים, eigenvectors, vector מצמיעים. Alright?
Just X tilde, E ו-N, האינדקסים האלה מאיפה הם רצים? 3N?
Yes, so all of those indices run from 1 to 3n. From 1 to 3n. I run over all the possible coordinates and I take derivatives with all those possible coordinates. Okay?
ו-U זה בעצם האנרגיה שמתחשב בה גם באינטראקציה.
Yes. U is the total potential energy where all the particles interact with any particles. Look on this guy over here. I take interactions of every two single particles inside my system. I just say, well, the only interactions that are important for me are the quadratic interactions. I don't take into account quadratic or whatever interactions that are my. All right. Yes. So there is a theorem that any symmetric function you can describe, that you can decompose in this form, and since A is symmetric, try to take a transpose of this guy and you will see that S minus 1 should be equal to S. It's because of the symmetric properties of Aij. Okay. If you really want, I can prove it. So this applies only if A. Yeah, something like that. So only if A is symmetric and it can be actually be diagonalized, then this representation applies. So all of this I want now to write down as, this is my H, is 1/2 M Z dot transpose plus zeta S D S minus 1 zeta. Okay. Now let's write it down a little bit differently. I would write it down as 1/2 of M zeta dot transpose plus zeta S multiplied by D. Transpose, yes, this is transpose, thank you. So this is S transpose, this is zeta transpose. Any questions? Yes?
What happened to U0?
Plus U0, but it doesn't matter. Okay, but you're right, let's write it down. But it's absolutely unimportant because
אפשר לשנות את נקודת הייחוס.
anywhere, always the energy is defined up to a constant. So it doesn't really matter what this U0 is. Okay, now, so we see that there is, I can say, well, this is a diagonal matrix. This is a vector multiplied by a matrix, so this is a vector. This is also a vector, okay, because I can write it down as some sort of a transpose of a vector multiplied by a matrix. Okay, the only problem is that I have vector of type A, vector of type A, and those are vectors of type D. So let's write it down such that this is U0 plus 1/2 M dot S minus 1 zeta dot transpose plus zeta S D zeta S, all of this transpose, right? So I have S transpose, zeta transpose, and I just simply say that this is zeta S and everything is transposed. Okay, now the nice thing is that this is S minus 1. All of those are independent of time, all those S's, right? Because they are the composition of this matrix, and this is constant because I took it as an expansion around the minimum. Right? S minus 1 is a transpose. So this is U0 plus 1/2 M zeta S, all of this dot, right? Because S is a constant, multiplied. Here I have S minus 1. I can write it down as S transpose. Here I have zeta dot transpose. I can take the dot out and make the transpose on the multiplication. So this is simply of zeta S transpose dot. Okay, and I have over here zeta S D, which is a diagonal, okay, which is a diagonal, and here I have zeta S transpose. Okay, so what I managed to do in all of those small dances on the board, my description now is of a diagonal system. Okay. Those particles are non-interacting. So if beforehand I had, look on this guy over here. This is my H. This was the original H, even when I took the expansion. Okay? And this is my final H. So here, all the particles are interacting. Well, there is a kinetic energy. Okay. This is a very kinetic energy. An interaction energy, which is the motion of degree of freedom number 1 is dependent on all the other degrees of freedom. They all together contributing to the energy. Now, here is a diagonal description. Why? Because this is a vector multiplied by a vector. So this is just kinetic energy. Okay. In different coordinates. What are the different coordinates? I have to take this zeta multiplied by some function S, okay? And those are my new coordinates. So this is kinetic energy, is just a sum. This term is the same vector, vector of positions, which are now new, multiplied by a diagonal matrix, multiplied by the same vector transpose. So here, if I'm looking on this description of a sum multiplied by sum, I will only have dxl, dxl. Okay, I won't have mixed terms because this is a diagonal multiplication. Okay. So what I learned from this, any system, I can expand around the minimal energy, and in some sense, my system always would like to sit in the minimal energy. We have shown this previously in thermodynamics. And I can describe it not in terms of single particles, because single particles were x tildes, right? I can describe it by new coordinates. I can make a specific transition. Okay? So if my original coordinates, were x tilde 1, x tilde 2, x tilde 3, okay, etc. x tilde 3n. Instead of, I'm looking on a vector which is zs, I can write it down as z1, z2, z3, up to z of 3n. Okay? And in those z coordinates, remember, each z is some linear function of all the different positions of all the different particles. This is true. Each z depends on all the different positions of all the different particles. But the Hamiltonian, this is what I obtained from here. The Hamiltonian is u0, which is not important, right, because it's a constant, plus 1/2 m, a sum from I from 1 to 3n of zi dot squared, plus a sum over I from 1 to 3n, okay, multiplied by di zi squared. This is my Hamiltonian in the new coordinates. This form, when I write it down in vector form, or when I write it down not in vector form but as a summation, this is how it looks like. Okay? And what we see here, this is already truly a sum over 3n harmonic oscillators. Right? You see, this is the description. This is the kinetic energy, it's quadratic, plus a sum, not a double sum, a single sum, because this matrix was a diagonal matrix, so this is only a single sum of di multiplied zi squared.
רגע, אנחנו רוצים ש-S זה קבוע.
S is constant because it's an expansion near the minimum. Yes?
How the hell are we supposed to diagonalize a 3n matrix?
Oh, this is a good question. So, and what is n, remember? What is n?
Very big.
Very big. So it's 10 to the 23. Right. So we can. You're absolutely right. We can. But Debye said, well, I don't care if you can or cannot. It is possible. Okay. So what Einstein described to us, this is true. This is absolutely true. There are 3n oscillating particles. But those particles are not the real particles. Those are real particles. You see? This is a position of, or degree of freedom of particle number 1. This also describes a particle. This also describes a particle. This is true. But actually, if you want to describe the system in terms of oscillators, what is oscillating, it's not particles, are those z's, right? And those z's are functions of all the positions of all the different particles. So you cannot simply say, well, I have particle 1 and particle 2 and they are oscillating somehow, and I don't really care they are oscillating, they are independent. Debye says, no, this is not true. What is oscillating are groups of particles that are linear functions of positions of all the particles inside the system. And they are the true oscillators. Okay. This is why we cannot simply say, well, we have 3n independent, identical, right? Identical particles. We have 3n independent, non-identical particles with what? With frequencies which are going to be different. How exactly to obtain those frequencies? Well, take this huge matrix A. It's going to be 10 to the 23 by 10 to the 23. Diagonalize it somehow. It's impossible even on the computers that we have nowadays. And then find those eigenvalues. Okay? And you're done. So this is impossible, right? It's impossible to diagonalize exactly. The only thing that we learn from it is that there is a description in terms of oscillators, and all the oscillators, the frequencies of all the oscillators are something. Okay, they are not identical. Nobody can tell us that this D, right, is an identity matrix. No, it's not. those D's are the eigenvalues of this A, and they can be whatever. I don't really know. So first part of Einstein is correct, but you need to consider vibrations, not single particles, of groups of particles. Those are waves. Second part is, well, the frequencies of oscillations are somehow must be determined. We cannot simply diagonalize, but because, as you said, it's impossible. So we need to find another way to obtain the descriptions of those D's over here. Now, by the way, all those particles that we are now treating are not regular particles. So these describe waves that we call phonons. Okay? Phonons. So those are the names, this is the name that we invent for our new fictitious particles. They're not single particle that is described by this coordinate z. Z is some general coordinate that depends on all the different coordinates of all the particles. It's not a single particle. It's a wave. And we call it and we use it as if it was a particle in mathematical sense. And we have a name for it. Phonon. Remember when I wrote to you the prescription of how we solve problem in statistical physics? Okay? There is only one route. The only route is to describe the system by a way that there are particles, fictitious particles usually, and that all those particles are independent. And this is what Debye built over here. It said, I can write a description, I don't yet know what these are, but I can write a description in terms of fictitious particles, and I will have a name from them. Those are phonons, and they describe the different waves, standing waves, okay, because they are not disappearing anywhere, that we have inside the system. Okay, so this is part number one. Part number two, what we do with those D's over here, right? Why do we need those D's? So all the particles now are independent. This is great, so we can use factorization. And the energy is just the sum of all the different energies that we have inside the system. So this is additivity. There are two terms or two conditions that must be satisfied in order for us to, in order for it to be possible to solve the problem. So additivity of the energy, check, okay? Independence of all the different particles in order to perform factorization, also check. This is great. So, so if we write, for example, Z1, okay, Z1, this is a partition function. Oh, we have the same Z. Call it Z tilde. Otherwise, we're going to be mixed with a lot of Z's. Z tilde. Yes? Because, well, the question is, why do we have 3n phonons? Well, because we started with 3n degrees of freedom, and because all of those are linear transformation, we end up still with 3n degrees of freedom. Conservation of the number of degrees of freedom that we have inside our system. That's it. You cannot get away with it. Yes. So the question is, Z1, will it be only dependent on x1 or x2, and Z2 is going to be only dependent on x3 and x4. So the answer is Z1 depends on everybody, and Z2 depends on everybody, and Z3 depends on somehow everybody. This is a linear transformation, okay? Find this matrix, take the original vector, multiply them, and you will get the exact dependence. Okay? But it's impossible because this matrix is too big. Okay, so the partition function. No, we don't know. We don't know who are the particles that contribute to Z1 and who are the particles. They all contribute somehow. Okay? This is the point. So the partition function of a specific particle. So what, and here Debye said, well, I will continue from here on as Einstein did, right? Einstein said the following. If you have a particle with frequency omega I, okay, so the different energies of this particle En, okay, are n h bar omega I. Okay, so those are the different energies. Then if I write down Zi, the partition function, it is a sum for n goes from 0 to infinity of e to the power minus beta and h bar omega I. Okay? We have seen it already several times, which is simply 1 divided by 1 minus e to the power minus beta h bar omega I. Okay? Now, if we want the whole partition function, so what is z? Z is a multiplication. I goes from 1 up to 3n of 1 over 1 minus e to the power minus beta h bar omega I. We don't know what all those different omega I are, because we are incapable of, or this A, incapable of finding those D's over here. We're simply incapable because the matrix is too huge. But what we can do the following trick. Okay. So first of all, this is a multiplication. This is what we can do with multiplication. But the physical quantity that is important is the free energy. Right? What is the free energy? Minus 1 over beta log of Z. Okay. Great. So what is F? So F minus 1 over beta log of phi I from 1 to 3n of log of Z. Okay. Which is 1 over beta minus 1 over beta. Like this. Log of a pi over 1 over 1 minus e to the power beta h bar omega I. Fine?
Yeah.
Alright. So minus 1 over beta of a sum, okay, over 1 over minus e ln. Thank you. Let's make it this. 1 minus e to the power minus beta h bar omega I. Minus disappears. Okay. This is the sum, and in order to solve it, I need to know what is exactly all the different omega i's are. Now Debye says the following: I don't know what the different omega i's are, but I know something about waves, and I assume that the spectrum of those waves is going to be continuous. There is going to be a continuous spectrum of the waves, basically saying that there is some density of states or densities of omega. Okay? So Debye says the following thing. All of this, in order to find this free energy, all of this is going to be 1 over beta, some integral, and we will find the limits of this integral, okay, of a log of 1 minus e to the power beta h bar omega, multiplied by the density of the different omegas that I will have, multiplied by d of omega. Okay, so this is continuous spectrum of omegas. Why do I think it's so? Well, I know something about the waves. I have been dealing with waves in my second year in my physics studies, and there was a full class about waves. There is some things about waves that they are continuous, so I'm going to use the continuous representation of omegas. The only thing that I need to find out is what is the density of states of the different omegas that I have. Now, this is already something to work with. Okay? First of all, we are not neglected interactions. The interactions were there because we're describing everything by different omegas that we have inside the particle. So the only thing that, and all the waves, they are indeed non-interacting, right? We usually assume that there is a superposition of waves inside any media, and the different waves, because we can separate them in terms of their frequency, they are not interacting with each other. least at the linear wave theory, and everything is fine over here. The only thing that's left is, well, what is this density? Okay, how we find it out? If we'll manage to find the exact expression for the density, okay, and we somehow figure out what are the limits over here, we're basically done. Yeah, we will have an integral that we need to solve, but it's already a technical problem. It's not a diagonalizing a function or a system of 10 to the 23 by 10 to the 23.
Stas,
Yes.
Are they summing over 3n particles? So why it's
But I'm summing over omegas. Every particle is contributing to what? To a different omega that I have inside. Okay, so I'm summing over all the different omegas that I have inside.
But we have 3n omegas inside. But
Yes.
there's a spectrum that they are chosen from.
Yes.
So why aren't summing
So
over
I
3n?
assume the Debye assumes that we will come to this. This is the limit from where to where you're assuming. So you're saying some of them are going to be from the lower parts of the spectrum. Some of them are going to be from the higher part of the spectrum. So Debye will assume that all of this comes from omega goes from 0 till some maximal omega. That is going to be the assumption of Debye. Okay? You need always to assume something because the system is too complex to take everything into account. Okay? So there is an assumption that usually the particles will prefer lower omegas than higher omegas. Okay? Now, why it is the intuition for choosing lower omegas and not higher omegas? Because of those terms. The higher the omega, the lower are the probabilities. So the system prefers to be in lower omegas, right? Because the free energy must be minimum. So if we are going to occupy all the higher omegas, it's not a minimal state.
רגע, אז אומגה זה בעצם ספור כל האומגה I שלנו?
No. Omega are the different frequencies of the z's that we have inside our system.
אז איך עשינו רק את המעבר מהסכום לאינטגרל?
This is the assumption. When omegas are continuous, this sum is going to be an integral. Okay, so now this part, I think at least you have seen a little bit. Or the TAs have shown it to you, but let's do it anyways. Okay. The density of waves frequency inside a box. So I need to assume something about my system. So usually I assume that my system is a box of size L by L by, what else do I have, by L. Okay, so this is my system, this is my solid. Now I'm looking on the waves that are living inside the system. Okay. So why I'm saying waves? Because all those Z's are somehow oscillating. They are not decaying. This oscillator still stays the same all the time. Right? The energy is a little bit more, a little bit less, but those are waves that are persistent inside the media. Basically, I'm basically saying I have a standing waves. And now I want to describe what is the density of standing waves inside a box. So the energy of a wave is h bar omega. Okay. Now the wave, the momentum, okay, of A is h bar multiplied by k, where k is the wave vector. Okay. What is k? 2 pi over lambda, which is the length of the vector of the wave, the wavelength length. Now, if I had, so now I want to eventually to look on a system which is a box, so it's a three-dimensional system. But if I had not a three-dimensional system, but a one-dimensional system, okay, I'm starting from 0, and the length of my system is exactly L. And I'm looking only on the waves that are standing waves. Okay. Only on the standing waves that somehow live inside my system. I know from boundary conditions, okay, that all the different wavelengths that are living inside my one-dimensional system has to satisfy the following formula. L divided by lambda over 2 equals to n, where n is an integer. Okay? So this is the description of standing waves. So if L divided by lambda over 2 equals n, what is the constraints? What are the constraints for K? Okay, so we have what? K equals 2 pi divided by lambda. Lambda equals to L divided by 2n equals to lambda. Right? So K equals to 2 pi divided by L multiplied by 2n. Blah, 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 blah. No 2? You are absolutely right. So those are the different Ks that I have inside my system. So if I'm looking on K, K can be what? Can be 1, right? If I'm looking on the sum of n. 1 and 2 and 3 and 4 and 5, okay, 7, etc., 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 up to n. How many states do I have here inside? It's just the number of points that I have written here, right? So if n is 7, the number of states is 7. If n is what? Pi, okay, what? N cannot be pi. If n is 8, the number of states is 8. So the total number of states, K, is what? Is always smaller than pi divided by L multiplied by n. Right? So I can say the following thing. That n, the number of states, is what? Is bigger than K L divided by pi. What are the K's? What you want to do this? Okay, equality. If the thing is that I wanted to tell you is the following. K satisfies this number. Okay, if I simply say what are the different number of K's that can be in my given system, it's going to be dependent on n. Right? So if n is 7, I can also have all the different K's that are satisfying this equation but with smaller n's. So the total number of states is not what exactly happening over 7, is 7, I forgot, and 6, and 5, and 3, and 2, and 1. So those are the different possible states that I have inside the system. It does not mean that K is one, specifically one of them, but it can be chosen out of all the different states. Now, this is the total number of states, and it is provided by what? By K. Okay. What is the density of states then? D of n. Well, let's write it of d of k, because the density of states is going to be dependent on k now, which is dn to d omega. And this is L divided by pi multiplied by dk by d omega. How I obtain density? I calculate the total number of states that I have inside my system, and it's all dependent on what? On the omega of the system, on the frequency, for a given frequency. I'm just taking the derivative of the total number of states with respect to this omega over here. Okay. This is very, very, very nice. Okay, but this is only for one dimension. What happens for 3 dimensions? What are the different cases that can be inside my system? If n equals 7, I can have also all the different cases that are satisfying this equation for lower n. That's it. I tell you what is n. It can be 8, it can be 9, it can be whatever you like. I'm just saying, if I choose n equals 9, what are the total number of states that are lying below it? Right? The total number of states, now how I define it, from 0, which is not a state, up to the number of states that I have chosen, which is dependent on my omega. Yes, because we obtain a general formula. What is this? For one dimension, for 1D, d omega is L divided by pi of dk to d omega. Okay? Now I can do the following thing for 2D or for 3D. What is d omega? I do exactly the same thing. I'm saying this, what is k? K now is a vector. Previously, what was k? K is a wave vector. I have been looking on one-dimensional system, and I've been looking only on standing waves in one-dimensional system. In 3 dimensions, because the waves are not interacting, it's going to be exactly the same for x, exactly the same for y, and exactly the same for z. So this is simply what? Pi over L multiplied by nx, ny, and nz. Now, instead of writing L, I'm simply saying this is pi divided by the V, which is volume, to the power 1/3, nx, ny, and nz. So all the cases that can be that are satisfying this, okay, is k multiplied by v to the 3rd divided by pi, okay, equals to nx, ny, and nz. nx squared plus ny squared plus nz squared. Square root. This is the size of k. This is the size of this vector, right? So what is the size of this vector? Which I simply write down as the absolute value of k. Okay? I multiply it by v to the 3rd divided by pi, and I have a square root, or I have a size of this vector. What is the size of the vector? X coordinate squared, y coordinate squared, plus z coordinate squared, square root of everything. So we have a specific nx, we have a specific ny, we have a specific nz that gives us a very specific wave vector. Okay? But this is a very specific one. Look what we have done here. We found a very specific n that provides us a very specific k. Okay? What we needed to do, we need to count all the states that lie below this k and then take a derivative. So how many states we have below this k is simply n, right? Simply n. Then we need to take a derivative of dk by d omega of all the total number of states. The same goes over here. We have a very specific k, which is provided by this value over here, which is specific nx squared plus a specific ny squared plus a specific nz squared. Okay? Now, how do you obtain the total number of states that are lying below this specific k that we have chosen over here?
Volume of the sphere, but
not exactly a sphere, but almost a sphere. So we write this ny. This is n. But we already have seen this trick of counting states, right? We're going from counting states to making an integral. N x, and we have n z, right? And all the different states are in the first quadrant, okay? In the first quadrant of this three-dimensional square. So imagine that I also filled everything here with dots. What are the different dots? The different possible state that we can have inside our system. Okay? So we have some sort of a 1/8 of a sphere. Okay. The volume in state space is 1/8 of the volume of a sphere with radius square root of nx squared plus ny squared plus nz squared. So all the different n's that are lying below, or they can contribute to k's that are below this specific k that we have chosen over here, is whatever is inside this 1/8 of the sphere. Okay. Now, what is the radius, or what is the volume of the sphere? So volume of the sphere is 4 divided by 3 pi r to the third. Okay. What is our r? So this is our r, which is equals to this guy. Okay. So the total number of states, which is whatever lies inside the sphere, number of states equals to 4 divided by 3 pi this guy to the third power, k v to the third divided by pi to the third power. Okay, this is the total number of states that we have inside our system. Why again do we have those discrete states? Because we're considering only standing waves. And we're considering all the standing waves that are capable of being inside my system up till we have a specific nx, a specific ny, and specific nz. And we must consider all of them. Why? Because this is the method how we find density. We compute the total number and take a derivative. Yes?
Don't we need to divide this by 8?
By 8. You are absolutely right. So this is what I have written over here. Okay. Now, we take a derivative of this guy. So d omega is, so here we have what? 2 by third. Right, so we have 2 pi of k squared, I'm sorry, 2 pi k squared v divided by pi to the third power multiplied by dk by d omega. This is our density of state. Yes.
למה אנחנו לא מתייחסים גם למיקום פה כשאנחנו עובדים?
There is no, those are waves. What is the position of a wave?
אין לו משהו.
And there is no positions for waves. We don't care about the positions anymore, right? Remember, what is the plan? We managed to separate everything into waves. We know that the different omegas, the frequencies of the waves, they are something. And we're trying to find the density of those different omegas. And this is how we do it. Okay? Yes?
Why are all the lengths exactly L?
Why? Well, because it's simpler to to go from here to the v to the third. But if they are not exactly the same, you will have to renormalize them a little bit. That's it.
Like, how do you know that you can normalize it? I mean, like L for all the...
Well, otherwise, this is a nice question for the exam. But otherwise, you're going to have what? You're going to have what? Pi by Lx, and pi by Ly, and pi by Lz, and you still do the same trick that I'm doing over here. Okay? You still do the same trick, exactly the same trick. You transform it everything to the some space state, and then you can compute there a specific part of the volume.
You like take it to where it's a perfect sphere, and then you can transform it.
Exactly, exactly. That's the deal. Eventually, you can always transform it. Transform it into some sphere, and then you can count the volume of the sphere, and you say the volume is the number of states. Remember, we did it with surfaces before. I'm just simply saying, well, each dot over here, which is a state, is what? Is a cube of 1 by 1 by 1 in state space. So by counting the total volume, I am counting the total number of different cubes that I have inside. Yes? Oh, what? Sorry? So this is 2 over here. 3. This is a full derivative. Okay, so let's, this and this disappears, and write it down. The omega is k squared by 2 pi squared v dk to d omega. Okay.
I got you, go.
Now, what is k of omega? What is called k of omega? Dispersion relation. And we usually know the dispersion relation for different systems. So k of omega is dispersion relation. The moment that you give me the dispersion relations for any material, I will take the derivative of this dispersion relation with respect to omega, okay? And I will have my density of state. Okay? Because if I know what k over omega is, I can find omega as a function of k. Okay? I will substitute omega as a function of k instead of k squared over here. I can take the derivative of k with respect to omega and will substitute it over here. Okay? And then I have the density of state. Now remember what we are looking for. The free energy is minus beta, an integral of log of 1 minus e to the power minus beta h bar omega d omega d omega. The moment I know the dispersion relation, I can perfectly well find all of this as a function of omega only, substitute it into this integral, okay? And that's it. I'm done. Okay? So out of all of this question of the bimodal, eventually I need to find what is the dispersion relation that I have inside my system. Exactly, you're right. You're right. You are absolutely right. So we need to find this and this guy. What is the dispersion relation? Or how we find it out? So in general, the dispersion relation, if you write omega as a function of k, okay, it can be whatever you want. The only thing that usually it starts something like this, but it really depends. This is omega over k as a function of k. It actually can be whatever you want it to be. There are different materials with different spectrums, and it's usually very complicated. And people invest a lot of time in compute it or measure it in an experiment. Okay, so we're a little bit lost. And here, Levi made the following assumptions. Okay, so all of this description, this is fine. Okay? This is really pretty, well, it's not straightforward, it's complicated, but eventually it's just a description in terms of waves. Not yet. Okay, so what is this? The problem, the physical problem is, what is this dispersion relation? Okay? How we find it out? Now, the assumption of Debye was as follows. If I have a wave that is propagating in a media, okay, the usual description or linear description of a wave is that I have a longitudinal wave that are propagating in the or they are oscillating in the direction of propagation, right? And usually I have, because if the direction of propagation is over here, I can only have one specific k that is oscillating in the direction of propagation. And I usually have two transversal waves that are oscillating in the direction which is transversal to the direction of the propagation. Okay, so if the wave is going in this direction, the oscillations are going to be orthogonal over here, over there. Okay, so this is transversal oscillations or transversal waves, and the wave that is oscillating in the direction of propagation is longitudinal wave. Debye said the following thing. I will assume that a linear connection between, for longitudinal waves, so we'll have v omega divided by CL, which is what? This is omega that I have, the frequency, and CL is the speed of propagation. So he said, well, I have one wave, which is what? Which is longitudinal, and I have two waves, which are transversal. Omega divided by CT, and I have another one, KT, omega divided by CT.
Those two KT are the same?
Sorry?
Those two KTs are the same?
Usually the CTs are the same. So usually the speed of propagation for waves that are transversal are the same. And longitudinal can be a little bit different. They are exactly the same. That are the two contributions. Yeah, transversal.
סטאס, זה לא רק לכיווני התקדמות. למה אנחנו מדברים על הגלים שמקבילים?
Because there is a connection between the size of the wave vector and the type of the wave. Right?
מה זה?
You can plug it inside. Right? I now have a linear description of case.
אבל אני רוצה רק את ה-K של ההתקדמות.
But this is a different. But it's separated into different. There are different contributions, right? There are different contributions. Exactly. Yeah, there are different contributions. So what is d over omega? Okay, so this is a general statement. This is a general statement. Now, let's assume, for simplicity, that all the CLs and CT and CT over here are exactly the same. They're exactly the same. So in general, K in any direction, I simply write it as omega divided by C. We have to remember that there is a speed for longitudinal waves and there is speed for transversal waves, but really don't care about it right now. Okay? Questions? No? Okay. So, what is d omega? We have to take into account three different contributions, right? Because we have waves that are longitudinals, we have waves that are transversal, and we have waves, another waves that are transversal. So in total, what we have, if you remember, for one single k, what was the formula? K divided by pi squared over 2. Volume was over here, right? dk to d omega. Now because I have three types of waves, three, not one, three, I multiplied it by 3. Why I simply multiply it by 3? Because I assume that all the different speeds of propagations are exactly the same. Otherwise, I have just to sum up the d omega for longitudinal, d omega of another transversal, and d omega of another transversal. So this is 3 of 2. Instead of k omega, what I have is omega divided by c squared, pi squared, volume, and dk to d omega. What is dk to d omega? 1 over c.
סטאס, למה אנחנו שהדיספרסיה היא לינארית?
This is the assumption of Debye.
זה באופן כללי...
So let me translate. Debye assumes that we are only looking on linear behavior of omega by k. And usually, this is the theory of linear response. For small enough case, you can always assume that the dispersion relation is linear. Okay? It won't work, and it never worked when k is large. It never works when k is large. Okay, so this is d omega. So we are, at least found this density of states, which is 3 by 2 of v divided by pi squared, c to the third power, and we have here omega squared. Alright, so if you look on this integral over here, this we know. Now we know this guy. Okay. Very nice. 2 additional parts are still unknown. Now, as I already told you before, Debye assumed that we only look on the states or the lowest states that are possible. We don't care about extremely high states of k. They contribute too much to the energy, and the system would like to be in its lowest energy states, not in the highest energy state. So those states that are lower are going to be occupied, or at least contribute. So we start from 0. Okay. And then Debye says, well, this is an assumption, right? This is what? The density of states is what? Is quadratic. So if this guy is quadratic, I cannot usually simply say that there is infinite upper bound over here. Okay? Debye said the following thing. I will assume that there is an upper bound, and I will call it omega Debye. Okay. Well, somebody else called it omega Debye, but there is an upper bound for this integral. Okay. And this we still don't know what it is. A lot of assumptions, right? So you see Einstein model, very, very simple. It's only like this, and then Debye model, and it does not work in low temperatures, and then you have to assume a lot of stuff, and the mathematics becomes much more cumbersome, and you have to take some intuition from the wave behavior, and then for how dispersion behavior works, and then that you have transversal and not transversal waves, etc., etc. It becomes extremely much more complicated the moment that you say, well, I have interaction. Well, yeah, you have interaction, and now you have to work really, really, really hard to describe it properly.
Can you explain again why the lower indentation is 0?
Because he says, well, the larger the omega, the higher is the energy, and I assume that my system prefers to be in lower energy states. Okay. So what Debye did? Debye said the following thing. We have d omega. We have omega. Debye says, I'm assuming that this is the behavior. The true behavior, I don't really care what it is, but the true behavior usually it will be quadratic, but then it somehow will deviate, or whatever. This is true behavior. Debye says, well, I don't really have a true behavior, I have a quadratic behavior, and if omega is not large enough, my true behavior probably is going to be described by what? By so this is the Debye assumption. This is how my waves behave, the density of my waves behave. This is omega, this is true, this is Debye, and we don't really know where to take this form, right? So Debye says, well, you have to stop it. You have to stop, and this is the upper bound in the integral, you have to stop it at some specific omega Debye. Why you have to stop it at a specific omega Debye? No, even simpler answer. Exactly. So the integral from 0 to infinity of d omega goes to infinity. Right? Because this is a quadratic function. So an integral over a quadratic function, and it's positive, is going to diverge. So this is why Debye said the following: no, 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 no. I have a constraint. What is my constraint? My constraint is that I perform my integration from 0 of d omega up to some specific omega Debye. It has to give the total number of states that I have inside my system. And what is this total number? It's 3n. Right? Because eventually I have 3n degrees of freedom, and if I sum over all the possible omegas that my different phonons are taking, okay, it has to give me the total number of degrees of freedom that I have in a system. Every degree of freedom has to be somewhere. And when I integrate over all of them, it has to produce the total number of degrees of freedom. So this is how you find omega Debye. Okay? So, and you cannot go over it. Right? This is the Debye's assumption. You also assumes a lot of physics in order to get this quadratic behavior of the density of state, and that it's continuous. He also says there is an upper limit, and the upper limit defined by this total number of particles that I have inside my system. No. So there are no constraints about this guy. It can be very large, very small. I don't really know what it is. But the total number of states has to be exactly equal to the total number of degrees of freedom. You cannot run away with it. It's like I told you, there is some sort of mass distribution inside my body. But I know that the total weight of my body is 75 kilograms. That's it. You know, the distribution can be whatever, but the total mass has to be equal to be 75. Because different omegas describe different degrees of freedom. Remember, each omega is one phonon. We started with 3n particles. We converted them into 3n phonons. Each omega is whatever phonon there is. You count all of them, and you have to get the 3n that you started with. Okay. This is, I don't know what it is. We will see. But the upper limit has to be, according to Debye, equal to whatever comes from this integral. Okay, so what is this integral? So what is the integral of 0 up to omega Debye of 3/2 v divided by pi squared c to the third omega squared d omega? Okay. So we take all of this out. We have 3/2 v pi squared c to the third 0 by omega Debye omega squared d omega, and this equals to 3/4 no 1/2 v by pi squared c to the third omega Debye to 1/3, and this equals to 3n. Because I'm thinking about the football match.
What?
I make a mistake and then I make excuses, that's all. Alright. Okay, so now I'm thinking about omega Debye is going to be connected to n to the 1/3. So omega Debye equals to, what do we have here? So we have 6, right? 6. We have pi squared. We have c to the third. We have divided by v, right? Divided by v. And we have n. And all of this to 1/3. Very nice. Then the free energy is equals to minus an integral from 0 up to omega d by log of 1 minus e to the power minus beta h bar omega of 6 pi squared c to the third divided by v. Omega squared, right? What was our omega squared? This, right? So this is multiplied by 3/2 v pi squared c to the third omega squared d omega, and that's it. Sorry? Where? Oh, 1 over b.
W שמצאנו עכשיו זה
Omega d by, yes.
הוא תלוי צורה, כאילו, או שזה כל פעם אני צריך לפתח את זה בצורה...
So the question is, what is this omega d by? So as long as I assume that all this CL and CT, remember these speeds of propagation of waves, are exactly the same, and we are working in 3 dimensions, this is always going to be the same result. Now, if I'm modifying it, for example, I will force you to do this to solve a problem in 1 dimension or in 2 dimensions, right? There is this dispersion relation. The d omega is going to be a little bit different. Then omega d by is going to be also different, right? So it depends on dimensionality, and it depends on how you use your dispersion relation, if it had the same speeds or not. That's it. So now we have the free energy is this integral, and we can go and find whatever we want. The only thing that we need to solve this integral properly, and the moment that we solve this integral properly, we know everything. Of course, we are now only dealing with canonical ensemble. In microcanonical ensemble, nothing of this works because there we need to solve extremely hard combinatorial problems that we are incapable of solving. Okay? So only in canonical ensemble we're capable of doing something. If we would have a microcanonical ensemble, nothing is possible. Okay, so what do we do next? The next thing is to start to take derivatives out of this integral somehow, in order to compute the different behaviors of CV, right? So first of all, what is CV? CV is du to dt. Okay. What is u? So there is a formula, right? So it is what is f? What is this guy?
F in TS, huh?
S minus TS. But this is complicated. So you're saying to me the following thing. So F equals to U minus TS. So I need to go to compute this guy and compute this guy, and somehow I'm going to obtain this U. This is too complicated. There are formulas, and U, remember, U is the average energy. So there is a connection between F and U that we have found. Okay. Or if you don't remember, so usually you have what? You have a lot of formulas. There are 8 pages of formulas or 4 pages of formulas that you have in exam. But if you don't remember, right? Usually it's very simple to say, well, let's use the connection between the average energy, okay, and the partition function. Remember? Let's assume that we have what? That we have a discrete spectrum, and there that we have z, okay, which is a sum over e to the minus beta ei. Here I have I. So if I want to compute u, u is a sum over I, ei, e to the power minus beta ei divided by z. Right? Remember the trick? So So 1 over z, a sum over I, ei, e to the power minus b, ei, it equals to 1 over z, a sum over I, minus beta, minus d to d beta, e to the power minus beta ei, equals to minus 1 over z, d to d beta, of a sum over I, e to the power minus b ei, it equals to 1 over z, d to d beta of z, and we obtain that u is minus d to d beta of ln of z. How it's connected to this guy over here? We're basically doing it all over again. Z is a multiplication, I from 1 to 3 n of 1 over 1 minus e to the power minus beta h bar omega I. Okay. Log of z is a sum, okay, over minus over log of 1 minus e to the power minus beta h bar omega I. We transform it into an integral, which is an integral minus 0 up to omega d pi of log of 1 minus e to the power minus beta h bar omega d over omega d omega. This is log of z. And remember, u is minus d to the d beta of log of z. Okay, so u is d to d beta of an integral of 0 over omega d pi of log of 1 minus e to the power minus beta h bar omega. Instead of d omega, you write this guy. 3 halves v pi squared c to the third omega squared d omega. And here we have u. So either you look in the notebook, either we have provided to you this the formula. Okay, usually the formula that's provided, it's this guy, and then you make this connection. So you don't have to rederive this, right? But this you will usually have to rederive, which is nice. Now we know that CV is du to dt. Okay. So eventually, in order to solve this problem, this is why we started. There was huge amount of math, huge amount of different assumptions on the way, right? Debye was famous because of all of this math and assumptions. But eventually, the quantity that can be verified in a lab, in an experiment, and this is what matters, is this specific heat, okay? Which is d to dt over d to d beta over this guy. Log of 1 minus e to the power minus beta h bar omega 3 halves v pi squared c to the third omega squared d omega. Okay. This is the formula that we have to compute. Omega d pi is already provided. Okay. And the moment that it's computed, we know if we were successful or not. Okay. And this is already easy. Why it's easy? Because, well, if I'm taking the derivative with respect to beta, the only thing that is affected is zi's, right? This guy, they are coming from the waves and the density of the waves and etc. etc. They are not related to temperature whatsoever. All the waves that I had in my system, they're waves. They were independent of the temperature. This is how we developed them. The only thing that was dependent on the temperature were the partition functions of the different phonons. They were important. So all of those derivatives are going to be dependent on what? On the derivative of this guy. And that's it. So actually, We will do this integral on Tuesday. So let's stop over here. I think we were already extremely tired. Yes. אתה מחמם קצת?